Here we're looking at the Wikipedia page of Harry Nyquist. He was born in Sweden. He moved to the United States when he was 18, went to the University of North Dakota for undergraduate degrees, which he completed in 2 years, then 1 year for a master's, and 2 more years, and he completed his PhD at Yale, where he worked on atomic spectroscopy. He then worked at AT&T Bell Labs for 37 years, making many interesting scientific contributions. We're most interested in his contribution to sampling theory. He showed that you could fully characterize a signal with minimal wavelength lambda if you make 2 samples per wavelength. That's Nyquist sampling. So here B is the maximum frequency in the signal, the bandpass, and as long as delta is 1 over 2, less than 1 over 2b, we can exactly reconstruct a signal. This slide's from episode 4 of our series. And we had here both a sampling strategy that we have to sample at the Nyquist rate and an interpolation strategy for how to exactly reconstruct the signal with the sinc function or the Shannon wavelet. The challenge of this theory is that it assumes that we can determine f of x equals n over 2b exactly. But when we make measurements in optical systems, we make a measurement that exists over some region of space or time, and we don't have the possibility of delta function sampling. Up till now, we've been talking about imaging in photographic systems using coherence functions and continuous distributions. But of course, when we actually build cameras, we get discrete pixels, and it's time for us to start talking about how discrete pixels work. Computational imaging. Episode 55, Discrete Sampling. Here's a simple model for a imaging system. So we have a object over here on the left. We have a lens system that's going to form an image of the object over here on the right, and we want to sample that image. We'll use a focal plane, which is an array of pixels. Each pixel has a photosensor in it, and we have a pixel pitch delta that we'll assume here. So as with anything in imaging systems, we need to begin by trying to make a forward model for exactly how the object is turned into data. And here's our basic forward model. So we have our object distribution f of x, y, and assuming here it's just a 2-dimensional distribution. And then we have our incoherent optical impulse response. So this is the optical response that maps the remote object field onto the optical distribution on the focal plane. And then we have a pixel sampling function. This describes how each pixel converts its local field distribution into a digital value. So the pixel sampling function could have any sort of form, and we'll get to that in a minute, but it's sampled at discrete points in space, and we've assumed here that we have a symmetric sampling in x and y. So delta is our pixel pitch, and we sample at discrete points, x equals to n delta or y equals my. Okay, so here we're facing the problem we talked about in the introduction, that we're not sampling the optical distribution at discrete points in space. We're sampling with this sampling function, but we can turn this into a sampling strategy that obeys the Nyquist Shannon sampling assumptions by considering a continuous function, g of x double prime, y double prime, where the object field is convolved with the optical response and also convolved continuously with the pixel response. And then the actual signal that we're measuring is in fact this distribution, g of x prime, x double prime, y double prime, evaluated at these discrete points, x equals to n delta and y equals to m delta. So we have in fact achieved a discrete sampling of the signal as convolved with the optical response and the pixel response, and both the optical response and the pixel response will implement some kind of a bandpass on the system. So if we look at this again, here's our general transformation of the signal from the object distribution to the measurements. We could integrate first over the prime variables, so the object field doesn't depend on that. And with respect to the prime variables, we get a system impulse response, which is the convolution of the optical response with the pixel response. Okay, so now this is a shift invariant linear system with the impulse response consisting of jointly the optical impulse response and the pixel response convolved with each other. We can take the Fourier transform of this shift invariant linear system and then the Fourier transform of the system impulse response, since it's the convolution of the optical response, and the pixel response is the product of their Fourier transforms. So the spatial spectrum of the signal that we measure is the spatial spectrum of the object field multiplied by the transfer functions due to the optics and due to the pixel. So we can model what this behavior looks like. And so one of the Jupyter notebooks that's on our GitHub site looks at this system transfer function. Here's an example. Let's say that in this top case, the pixel pitch is lambda f number divided by 2. What we have here on the left is the pixel transfer function. This is the Fourier transform. We've assumed that the pixel is defined by a rect. So we have a square pixel. This p of x, y would be rect of x times rect of y for some pixel pitch delta. Okay, so that's its transfer function. Now, if we multiply this transfer function with the optical transfer function, which as we've seen has this kind of conic shape, we get this. Looks a lot like the original optical transfer function. Turns out that the impact, if we sample at or below Nyquist, is not large. If we sample at something that is less than the Nyquist rate, here we make our pixel pitch equal to 2 lambda f number. Then we see that on this same scale of 1 over lambda f number, we see that the bandpass of the pixel is much less. And if we plot here the system transfer function, where again the units here are 1 over lambda f number. So that's why the extent goes out to 1 over lambda f number equal 1 up here. Down here you see that the system transfer function is reduced. If we undersample, the system becomes band limited by the pixel instead of by the optics. Conventionally, we look at the transfer function along an axis. Here, this is the x-axis in frequency space, and we're looking at the system transfer function for various sampling periods. The top curve, the blue curve, corresponds to just the optical transfer function, so it's not modulated by the pixel transfer function at all. The next one, the yellow curve, corresponds to oversampling by a factor of 2, so that this delta is equal to 0.25 times lambda f number, which is half of the Nyquist period. The green one is for sampling at Nyquist, and so both the yellow and the green, you don't see a lot of impact on the system response going out to the maximum frequency of 1 over lambda f number. The red curve corresponds to sampling at with a sampling period of lambda f number, which is twice the Nyquist period, and then the purple curve is 4 times the Nyquist period, sampling it with a period of 2 lambda f number. And here you're seeing the spatial frequency response drop as we increase our sampling period, and the effect of pixel modulation becomes more pronounced. But it's important to also remember that as we decrease our sampling rate, that the Nyquist period, the Nyquist frequency also changes, and so we'll see impact from aliasing as well. It's easiest to understand the impact of aliasing if we plot the system transfer function as a function of 1 over the pixel pitch delta for various values of lambda f number. The top curve here, the yellow curve, corresponds to lambda f number equal delta over 2. So delta is equal to 2 times lambda f number. And we've undersampled relative to the optical transfer function by a factor of 4. The blue curve corresponds to lambda f number equal to delta. So we've undersampled relative to the optical bandpass by a factor of 2. And the bottom curve, the green curve, corresponds to delta equal to lambda f number over 2, or lambda f number equal to 2 times delta, meaning that we've sampled at exactly the Nyquist frequency for the optical response. So the Nyquist frequency for pixel pitch delta is 0.5 over delta. So the aliasing occurs to all frequencies to the right. Over here, this would all be aliased. If we sample at exactly the Nyquist frequency for the optical transfer function, there is no aliasing because the optical transfer function goes to 0 at the aliasing limit. If we undersample, as shown here, for these other two cases, spatial frequencies to the right over here would alias into lower spatial frequencies in the apparent image. This ratio of the lambda f number divided by delta has a name. It's called the Q factor, and so the Q, if Q is equal to 2, that's exactly at Nyquist, where lambda f number is equal to the pixel pitch divided by 2. And then we have these other values, and so the setting of Q is an important parameter in designing optical imaging systems. As you see in this image from this great book by Robert Fiente on the imaging chain of digital cameras, that on the left we see a blurry image if the image is limited by optics. On the right we see a pixelated image if the the resolution is limited by the pixel sampling instead, and in the middle you see some balance. So setting Q equal to 2 is exactly matching the bandpass of the optics to the sampling. Q greater than 2 means you're oversampling, and Q less than 2 means you're undersampling. But typically you may choose to oversample or undersample. One reason to oversample is that the image consists not just of spatial data but also of color. So if you wanted to avoid problems due to having to demosaic the color, you may choose to oversample, and you may choose to undersample because of, number one, there's a cost to sampling data, right? If you double the image resolution, that means twice as many pixels you have to read out. Each pixel requires power in the imaging system, and so it may not be worth the extra effort to just get rid of aliasing. Here's some simulations from the GitHub notebook showing, first of all, a chirp signal at the top, and then the next line shows that we've sampled at the Nyquist rate for the optical bandpass, and you see that the roll off in the contrast consistent with that. The maximum frequency here corresponds to 1 over lambda f number, so you get almost to the maximum frequency but a continuous roll off. And then if we undersample by a factor of 2, as in this third line, you see these high frequencies in this region occur as alias frequencies here, that they appear as lower frequencies than they are. And then here we've undersampled by a factor of 4, and that becomes much more pronounced, that we see these aliasing artifacts from high frequencies, and a null here corresponding to a null. These nulls, occur in the pixel transfer function. The optical transfer function has a smooth monatomic roll off, but the pixel transfer function has the sync-like behavior that can create nulls and then aliased artifacts. It's not necessarily true, however, that you would choose to do this line because the aliasing artifacts are not the only cause of noise in these systems and not the only expense. So here's an example where we've added Poisson noise to these signals, and what you see is that there is more noise at low frequencies in the signal that's sampled at the Nyquist rate than there is in the signal that is undersampled. That's because the undersampled signal at the low spatial frequencies has a higher effective bandpass, as we saw a couple slides ago, and so with this higher transfer function has less noise at low frequencies. So as with all things in computational imaging, there's some trade-offs here that we need to consider as we get into the design of these systems. But now you have the mathematical tools to model and understand that. Here's a slightly more complex image, and you can see aliasing creates these kind of non-uniform artifacts in the undersampled signals. Here's cross sections of the signal showing what the samples look like. Now, what we're showing you here is the raw pixel values. So we measured these values G and M. The Nyquist-Shannon sampling theorem provides not only a sampling rate that you need to represent the signal, it provides an interpolation strategy. So here's an example of a signal that has different phases. This is a cosinusoidal signal that's at the same signal, but the phase is shifted, and you see the data looks different as the phase shifts. But if you take this data, exactly this data from these plots, and interpolate it using this Shannon interpolation formula, you can see that the interpolated signals all look exactly the same because they are in fact the same signal. What this means for digital imaging is that basically your raw pixel values are far from your best representation of the signal that you've sampled. So after we've talked in this episode about how to model the sample data in terms of the spatial frequencies of the signal. Now we have our model for what the samples G and M are. Our next question is, how do we turn those into images that we would want to display? And we'll talk about that in the next episode.